Hi, my name is Karolina Porcelli, and my project is an in vivo study using Caenorhabditis elegans to determine the potential effectiveness of vitamin D3 and docosahexaenoic acid for the treatment of Parkinson's disease. Parkinson's disease is the second most common neurodegenerative disorder and most common movement disorder in the United States. Globally, the prevalence of Parkinson's disease has doubled in the past 25 years, with 8.5 million people suffering from the disease in 2019, according to estimates by the World Health Organization. Furthermore, Parkinson's disease resulted in 329,000 deaths globally in 2019, an increase of over 100% since 2000. Unfortunately, due to an aging global population, the prevalence of Parkinson's disease is expected to double by 2040. Parkinson's disease is caused by the loss of dopaminergic neurons in the substantia nigra region of the brain, resulting in reduced levels of dopamine. The disease is characterized by motor symptoms and non-motor symptoms that significantly lower a patient's quality of life and decrease life expectancy. Despite the significant morbidity and mortality of Parkinson's disease, adequate treatment for slowing the progression of the disease and for alleviating the symptoms in those with advanced Parkinson's disease is lacking. All current treatment options, including the gold standard levodopa, decline in effectiveness over time and eventually become ineffective at managing symptoms. Moreover, many of the current treatment options have severe side effects that can frequently become so intolerable that the treatment must be discontinued. In addition, there is a lack of access to standard treatment for those in developing countries and for minorities in developed countries. In 2017, the World Health Organization Neurology Atlas examined neurological care in 132 countries and 2 territories comprising 94% of the world's population and found that consistent access to levodopa in primary care was only available in 34% of the countries surveyed, none of which were developing countries. Furthermore, even when levodopa is available, it is often unaffordable and not covered by public health insurance in developing countries. In regards to minorities in developed countries, Dr. Nabila Dahodwala at the University of Pennsylvania Perelman School of Medicine found that African Americans are 4 times less likely than Caucasians to receive adequate treatment for Parkinson's disease. In light of the limitations of the current treatment options, new affordable and accessible treatments for Parkinson's disease should be developed. Nutraceuticals have become increasingly popular as affordable and safer alternatives to conventional treatments. Scientific literature suggests that vitamin D3 and DHA, an omega-3 fatty acid, could potentially increase dopamine levels in the brain. This led me to investigate whether vitamin D3 and DHA could be used as effective and safer alternatives for the treatment of Parkinson's disease. An in vivo study in the organism C. elegans was conducted to measure the effects of supplementation with vitamin D3 or DHA on dopamine levels. Chemotaxis assays were performed to measure the olfaction-based movement of C. elegans away from 1-nonanol, a chemical with a strong fruity odor. Chemotaxis indices were calculated to quantify the dopamine levels of the organism. C. elegans is a microscopic roundworm that is used as a model organism for studying neurodegenerative disorders because it has the most well-defined nervous system of all organisms and can exhibit a loss of dopamine neurons and a disruption of dopamine-dependent behaviors. Most importantly, C. elegans shares a large portion of its genome with humans. Therefore, there is high translational potential of C. elegans studies to human health. The chemotaxis assay is an established method for the indirect measurement of dopamine levels because dopamine signaling is involved in the olfaction-based movement of C. elegans away from 1-nonanol. I developed the research idea and the entire procedure independently. The initial steps of the procedure were conducted at the Dishaw Lab, a designated BSL-2 lab at the USF Morsani College of Medicine. The qualified scientist was provided with and precisely followed the procedures I developed. First, 1,000 micromolar vitamin D3 and DHA stock solutions were made. These were then used to make 250, 400, and 500 micromolar vitamin D3 test solutions and 50, 100, and 150 micromolar DHA test solutions. The control solution was 95% ethanol, since 95% ethanol was used to make both the vitamin D3 and DHA solutions. Second, 35 petri dishes and 35 square agar plates were poured with nematode growth media and labeled to be used for 5 trials of each test solution and 5 trials of the control solution. Then, 0.1 ml of heat-killed and concentrated E. coli OP50 was applied to each NGM petri dish to serve as nutrition for the C. elegans. Each labeled OP50 seeded NGM plate was then covered with 100 microliters of the corresponding solution and left to sit overnight. Age-synchronized C. elegans were prepared by placing 10 adult hermaphrodites on each of the OP50 seeded NGM plates covered with the solutions. After 4 hours, the adult hermaphrodites were removed. This incubation period allowed adult hermaphrodites to produce offspring of the same age, thus reducing confounding. These plates were then incubated for 2 to 3 days until the worms reached the young adult stage of their life cycle. Once the C. elegans reached the young adult stage of their life cycle, as observed under the compound light microscope, the chemotaxis assays were conducted. Chemotaxis assay plates were divided into odor and reference sections and labeled according to the image. A worm suspension was prepared for each assay by collecting the worms from the appropriate petri dish and performing 4 S-basal washes to remove any possible E. coli present. The worm suspension was placed on the chemotaxis plate at the location shown in the image. Then, a 1% 1-nonanol solution was spotted onto the plate in the location shown in the image. The number of worms in the reference and odor sections were counted at 10 minutes and at 30 minutes under the dissecting microscope. Here are some images of my procedure. Here are some images of the C. elegans during the chemotaxis assays. These tables show the number of worms in the odor and reference sections at 10 minutes and at 30 minutes for each group of C. elegans. A chemotaxis index was calculated for each trial by dividing the difference between the number of worms in the odor section and the number of worms in the reference section by the total number of worms in the two sections. These tables show the chemotaxis index values of each group of C. elegans at 10 minutes and at 30 minutes. The graph shows the mean chemotaxis index values of each group at 10 minutes and at 30 minutes. As you can see, the mean chemotaxis index value of each vitamin D3 and DHA group was more negative than that of the control group, indicating higher dopamine levels in the supplemented C. elegans. To see if the differences in the mean chemotaxis index values were statistically significant, a NOVA and Tukey HSD statistical tests were done. Although some of the 10-minute p-values were not statistically significant, all of the 30-minute p-values were highly significant. Therefore, I concluded that vitamin D3 and DHA can increase dopamine levels, demonstrating their potential effectiveness for the treatment of Parkinson's disease. Real-world applications of this study would be the use of vitamin D3 and DHA in the treatment of Parkinson's disease. They could potentially be used in addition to the current treatment standards, as alternatives for those who cannot tolerate the side effects of the current treatment standards, or as more affordable and accessible treatment options in developing countries.